For the first speaker, we have Andrea Basso, who is going to make an introduction to ski sign, which will make everybody more at ease with the rest of the session. How about let's welcome Andrea.
Hi, everyone. Thanks for the introduction. Yeah, as you may have seen from the program, there is going to be 3 talks on ski sign using 2-dimensional techniques. So we thought it might be beneficial to have an introductory session where, with a high-level accessible description of ski sign, what it is, how it works, and how the different versions of ski sign that appeared in the literature so far differ from each other. At the very core of ski sign are isogenies and elliptic curves. And isogenies are maps between elliptic curves, and you can think of this as a one-way function. They're easy to compute, but they're hard to invert, in the sense that given 2 elliptic curves, it's generally hard to find a connecting isogeny. And in particular, we're also interested in a very special type of isogenies, which are isogenies that start from a curve and end up in the same curve. And we call these endomorphisms. And the endomorphisms of a given curve have a special structure, which we call an endomorphism ring, which is a 4-dimensional object when we see it as a lattice. Because if we have 4 linearly independent endomorphisms, these spawn the entire ring. And these 2 are the fundamental problems, hardness assumptions in isogeny-based crypto. On one end, if we are given 2 curves, finding a connecting isogeny is hard. And at the same time, if you're given a single curve, finding one endomorphism or finding the entire endomorphism, it's similarly hard. And these 2 are the 2 fundamental assumptions, but luckily for us, they are equivalent. So let me elaborate a little bit on what I mean with equivalent, because the algorithms that allows us to construct these equivalents are precisely the algorithms that power ski sign. Let's say that we start from a curve and we're also given its endomorphism ring. If we know an isogeny departing from this curve, then we can also use this. We can use this information to compute the endomorphism ring of the target curve. So the main takeaway from this algorithm is that isogenies allow us to carry the knowledge of the endomorphism ring from the starting curve to the end curve. Conversely, if we are given 2 curves and we're given the endomorphism rings of both curves, then we also have an algorithm that allows us to find a connecting isogeny in polynomial time. So in some sense, endomorphism rings act as a trapdoor, which make the isogeny finding problem, which is generally hard, easy. And with these 2 algorithms, then we can actually build the ski sign protocol. Let's look at the identification protocol for simplicity, from which we can obtain the signature using standard Fiat-Shamir. And we start from a curve whose endomorphism ring is publicly known. Then, to construct a public key, we sample a random isogeny, which will be our secret key, and we end on a curve which will be our public key. Then, because we know the endomorphism ring of the starting curve and we know the connecting isogeny, we can also privately obtain the endomorphism ring of the public key. Since this is a sigma protocol, we start with then making a commitment, which consists of sampling another isogeny, a commitment isogeny. The commitment then consists of the end curve of this commitment isogeny. And similarly to before, we can also privately obtain the endomorphism ring of this curve. Then we receive a challenge from the challenger in the form of an isogeny starting from the public key. This isogeny is known, is public, and because of that, then we can also translate the knowledge of the endomorphism ring on the public key onto the challenge curve. Once we do this, then we know the endomorphism ring of on the commitment curve and on the challenge curve. So as we've seen in the previous slide, this means that we can easily find a connecting isogeny, which will be our response. Then verification simply consists in checking that this response isogeny actually starts from the challenge curve and ends on the commitment curve. And this is the very high-level view of how SkiSign works, and this encompasses all variants that will be presented today, as well as all the variants that have appeared in the literature so far. But before we go further, we need to sort of delve deep a little bit more on how we represent isogenies and how we work with them. Usually, we start from a point on an elliptic curve. We consider the subgroup generated by this point, and we have a one-to-one relationship between the groups on the elliptic curves and the isogenies. And when we do this, the cost is usually linear in the size of the group, which is also how many isogenies we have, which means that if we want enough security, we want exponentially many isogenies, but using this sort of straightforward approach also means that computing such an isogeny is exponentially costly. So the usual solution is that we restrict ourselves to consider isogenies that are polynomial time, that have very smooth size, say, for instance, L to the E. And when we do that, then in that specific case, we can divide the isogeny into smaller chunks, into specifically E chunks, where the size of the subgroups associated with one of them is L. And then the computation becomes much smaller and polynomial time, because then the cost is simply repeating E times something that is very small and very efficient. But then the natural question is, what happens if the size of G is prime or simply is not smooth? Then for the longest time, we didn't really know how to do this in the general case at least. But luckily for us, 2 years ago, as a byproduct of the attacks on SIDH, we developed new tools that allow us to represent and work with such isogenies, and we call this a higher dimensional representation, which allows us to represent an isogeny simply by describing the start and end curve and how this isogeny acts on certain points. In some sense, this is similar to polynomial interpolation, because in the same way that you can represent a polynomial by knowing sufficiently many evaluations of the polynomial, in this case, by knowing how the isogeny acts on sufficiently many points, we can recover this isogeny and work with it. And here we have different cases for how this computation actually costs. But generally, if the size of G has this specific shape of Q times N minus Q, then we are in the so-called two-dimensional case, which is fairly efficient. And in all other cases, the computational cost is doable maybe, but like much more expensive. So that being said, now we can look at how the one-dimensional version of SkiSign work, which is the first proposal of SkiSign, and it's currently what's being submitted to the NIST additional call for post-quantum signatures. And because at the time we only knew how to work with smooth degree isogenies, then we necessarily have to work with responses that are smooth degree. To do so, we use one specific algorithm, which we call KLPT. How it exactly works doesn't really matter. We can sort of take it as a magic black box, which takes into input the endomorphism ring of the commitment curve and the endomorphism ring of the challenge curve, and produces a connecting isogeny of smooth degree. And in particular, the degree, the size of the group associated with it will be a power of 2. When we do this, however, the cost is particularly high because the isogeny that it produces is very long, much longer than what the theoretical minimum would be. And because of this, then the whole procedure tends to be very slow. So indeed, if you look at SkiSign in one dimension, you see that the signing is much slower than the verification, which will simply consist of recomputing this isogeny. Then, just last year, ski sign HD was introduced that relied on this higher dimensional representations. The idea is that we no longer are restricted to using smooth degree responses, but instead we can represent responses of any degree by using this 4-dimensional representation. And the idea here is that rather than using the very expensive KLPT algorithm, instead we use LLL. This is the same LLL that you may know from lattice-based cryptography for basis reduction. The reason for that is that before I mentioned that the endomorphism ring can be viewed as a 4-dimensional lattice, but because of that, we can also construct the set of all the possible isogenies between two given curves, and this will also form a lattice of dimension 4, which means that we can then run LLL to obtain a short basis of this lattice, and we can then use this short basis to find a short element, which will then correspond to a short response. And this works exactly in the same way. It takes the two endomorphisms, computes this lattice, reduces the basis, and produces the short element. And now the response is nearly what is theoretically optimal, and it is indeed much shorter. And because of this, the computation for producing this response isogeny, which is what is used during the signing, is much, much faster. The downside of this approach is that because we have no control on the degree of the response, we are forced to use 4-dimensional isogeny, 4-dimensional representations, which tend to be fairly inefficient, which means that then the verification in this case tends to be relatively slow. So for the rest of this session, you'll hear a lot about ski sign 2D, which is a version of ski sign that uses 2-dimensional representations. And as I mentioned before, to represent an isogeny in 2 dimensions, we need this kind of condition on the response that has this very specific shape. And the idea is that, once again, we start exactly as before. We run LLL, and we obtain a response for which we have no control over its degree. So let's say this is then of degree 2. Then, after that, we sample a random isogeny starting from the commitment curve of degree 2 to the a minus q. And luckily for us, the degrees are multiplicative, which means that if we look at this composition of these two isogenies, they form an isogeny of the degree that we want specifically, which means that we can then represent it in dimension 2. Now, if we do this, we obtain a response that is still much shorter than what we have in the 1-dimensional case. It is going to be slightly longer than the HD case because we have this additional component, but it still be much shorter than what we previously had. LLL is still very fast and very efficient compared to the KLPT. And at the same time, we get to use a 2-dimensional representation, which is much, much faster than what we have in the 4-dimensional case. And this is sort of a very high-level view of what ski sign 2D looks like, but several improvements and iterations had to go into making this possible, including the algorithm to efficiently sample this additional 2 to the a minus q isogeny, as well as many other decisions and many other choices that you will see presented in the rest of this session. So just to quickly give you a comparison between the original ski sign in 1 dimension, the ski sign in HD, and the ski sign 2D. And when I say ski sign 2D here, I mean generally what emerges from the 3 versions that you'll hear about today, even if, of course, they all have their differences and they might be have slightly different entries in this table. If we do that, then we'll see that well, I can tell you. If we look at, we can see that the signature size remain pretty small across the board. All 3 variants have very small signatures, and indeed these are the smallest post-quantum signatures from any kind of type of assumption. We have that the signing time of ski sign 2D is comparable to that of HD, even if significantly slower than what we previously had in one dimension. And at the same time, verification is also equally efficient as in the 1D case. So in some sense, the 2D construction allows us to interpolate and obtain the best of both worlds, where we gain the same improvements that we had from the HD case, while also keeping the improvements or the benefits that the original construction had. There is some bug. That's good. Okay, in any case, besides the efficiency of the signing and the verification, the 2D variant also manages to improve on the previous versions by having a much cleaner security definition and security view, and relies on much weaker assumptions and much more standard assumptions. And in the same way as the HD variant, it allows us for much better scalability across all parameters and security levels in a more straightforward fashion. So I think I'll just conclude. You'll hear a lot more about SkiSign 2D in, okay. So this was the table I was telling you about. If you take a quick recap, a quick look, you'll see that the original SkiSign did fairly well on signature size and verification efficiency, whereas the rest was so-so at best. The HD variant managed to drastically improve the signing efficiency and the security and scalability at the cost of verification efficiency. And finally, the 2D that you'll hear about today manages to get the best of both by having good signature sizes, decent signing efficiency, really good verification efficiency, as well as maintaining the same security and scalability properties of the HD variant. So once again, you'll hear a lot more about SkiSign 2D today, so I won't say anything more. But in general, if there is one takeaway, is that the 2D variant allows us to use the efficiency of 2D representations while also maintaining all the benefits that the HD variant introduced. The security profile is much cleaner and much nicer than what we used to have, especially relying on weaker assumption than the one-dimensional case. And lastly, over the last couple of years, we've seen an incredible amount of improvement for SkiSign, mainly thanks to the introduction of these higher dimensional representations, which makes it natural to wonder what's going to come next. How much is it going to still improve over the next few years? Thank you very much for your attention.
Thank you for Andrea. That's
Can you explain in the table what do you mean by scalability again of the signatures?
Yeah, so the main parameter in all of this construction is the prime characteristic where you're doing all your computations in. And in the original construction, the prime that was required had a very, very specific shape. Basically, you required that this prime satisfied that p squared minus 1 was very, very smooth for some definition of smoothness, which meant that finding larger and larger primes was a computationally demanding task. So finding parameters for higher security levels was doable, but required a lot of computations, and it was, in some sense, a limiting factor. Whereas what we have in this both HD variant and 2D variant is that we use primes that are much, much easier to find and can be basically found instantly, so that it's much easier to scale to different security levels and to choose whichever prime makes computations easier, rather than having to depend on precisely what this costly prime finding search produces.
Thank you.
Any other questions? If not, let's thank Andrea. And we have next up Luciano Meno.
Hello? Okay, yes, it works. Yes, so thanks for the introduction. So today I'm gonna talk about, the SkiSign2D West version, which is the fast, the small, and the safer. This is joint work with Andrea Basso, who gave like such a nice introduction. So I guess that right now we are all familiar with, the world of isogeny, so we know everything about isogenies. And my other co-authors, Pierrick Dartois, Luca De Feo, Antonin Leroux, Giacomo Pope, Damien Robert, and Benjamin Wesolowski. So the first thing that we should, do is to understand what does it mean. Why do we need another variant of SkiSign, and what's the point of all, all the words that we put in the title? Why is it the past? Because I mean, together with SkiSign2D East, at the moment, this is actually, sorry. This is at the moment the fastest variant of SkiSign. And here, like in the paper, we have actually two variants for SkiSign2D West. One is kind of the most secure, where we know we have sort of like some conservative assumptions. So we are not really aggressive with our parameter choices. And also we have another variant, which is a little bit more heuristic. In the case of the heuristic variant, we also have like kind of a twofold speed up on the signing algorithm. But for the rest of the talk, I'm gonna focus on the rigorous one. And it's the small, because I mean, as Andrea was mentioning, actually, SkiSign has this really nice feature, which is incredibly compact. What does it mean? Can we actually have some concrete numbers? Yeah, let's take a look at the NIST security level. So for public key, for level 1, we already have like 66 bytes. And then it scales to level 398 and 130 for level 5. And whereas for signature size, we have 148 for level 1, 222, and 294, respectively. And then the last feature, this is actually for us like the most important one. This version is actually the safer. What it means that thanks to some subroutines that I will explain to you like in the next slides, we obtain like a version of SkiSign which is probably secure. And this is something that we are really proud of, and something that we really that's actually the message that we want to convey. That right now, like SkiSign relies on very few heuristics. Okay, so I said that at the moment we have kind of the the safest variant of like SkiSign. And how did we achieve so? So first of all, I'm going to introduce to you like some new building blocks and like new techniques that appeared in the field of isogeny-based cryptography. The first technique is actually a really nice trick by Nakagawa and Onuki. And this is like a way to compute isogenies of fixed degree. So first of all, let's fix like the setup where we are gonna talk. So we have E0, which is actually this very special supersingular curve. This is the curve with J invariant 1728. And the characteristic of like our base field is actually prime P of the form C times 2 to the D minus 1, where C is just like a small positive integer. And why is this curve so special? Because, I mean, the endomorphism ring of this curve enjoys a really nice form. And for the moment, let's define this endomorphism ring to be O0. And this algorithm, called like fixed degree isogeny, takes as an input like an odd integer, which is like smaller than 2 to the e, and outputs an isogeny phi u of degree u. In the previous talk, Andrea explained that the complexity of computing isogenies actually depends on the size of the kernel and the smoothness of the kernel. With this new technique, we don't care at all about the smoothness of our, like the degree of the isogeny. And in practice, whenever we start from this special curve E0, we actually have an efficient way, an efficient way to compute these isogenies of like non-smooth degree. And this is a really nice trick, really nice idea. Then using this idea, we came up with like this new algorithm to convert ideals to isogenies. In the previous talk, Andrea was explaining to you that endomorphism ring have this lattice structure. And whenever we have the endomorphism ring of two elliptic curves, we can actually find a connecting isogenies for like the respective elliptic curves. How do you do so? The idea is that isogenies correspond to ideals. So it's true. I mean, this is true. This is a result due thanks which was obtained using like the Doring correspondence. But even though this is kind of theoretical result, we still have to, to concretely convert between ideals and isogenies. In the previous versions of SkiSign, this was kind of a demanding task, and there were like several tricks to make this conversion as fast as possible. Here in this new version of SkiSign, we come up with a new way to convert like ideals to isogenies. And the most interesting feature of this new algorithm is that you have basically no restrictions on the idea on the ideals you want to convert. So basically, you don't require them to be smooth. You just take an ideal, you convert it to an isogeny. And okay, let's go through like the details of like this algorithm. So the first step is like taking this ideal I, this is like the ideal that we want to convert to an isogeny. We find two equivalent ideals, I1 and I2, such that there exist like two values, u and b, two positive integers, verifying this equation here. U times the norm of I1 plus b, the norm of I2, is equal to a power of 2. The reason why we want that these values sum up to a power of 2 is because, I mean, we want to be efficient when we convert these isogenies to, we convert these ideals to isogenies. And then the additional requirement is that the GCD between U and the norm of I1 and the GCD of B and the norm of I2 is equal to 1. Once we find these ideals, and we know that I1 and I2 are actually equivalent to I, it means that there exist like two endomorphisms, beta 1 and beta 2, such that I1 is equal to I, the conjugate of beta 1 over the norm of I, and the same holds for I2, where we use like the endomorphism beta 2. Then, once we have like this way to represent these equivalent ideals, what we want to do is to compute this endomorphism here, which is given by the composition of the isogeny associated corresponding to I1, composed with the dual of the isogeny corresponding to I2. This ideal, I mean, evaluating this isogeny can be a little bit complicated if you just want to evaluate each single component of this endomorphism. But if you look at the representation of these equivalent ideals, you can actually represent this endomorphism theta as beta 2 times the conjugate of beta 1 over the norm of I. And then you evaluate, using this trick, you can evaluate this endomorphism over the 2 to the torsion of E0. And then using like the algorithm that I was explaining you before, fixed degree isogeny, we compute two isogenies of degree U and V. And let's call these isogenies phi U and phi V. And then additionally, we look at these new isogenies connecting the curves EU and EV. And this isogeny is given by the dual of phi U composed with theta composed with phi V. And given that we know how to evaluate theta on the 2D torsion, we can evaluate this long isogeny on the 2D torsion of U as well. And then here comes the trick. We can extract the component of phi I1, the dual of phi U composed with phi I1, just by looking at like two-dimensional isogenies. Here I claim that, extracting this component is efficient because computing this two-dimensional isogeny is efficient, but I'm not explaining to you how we can compute these two-dimensional isogenies. If you want to know how to compute these isogenies, wait till Thursday, because there will be a talk about explaining how to compute like these isogenies. And then once you have this component here, from the isogeny phi I1, you can recover the isogeny phi I, which is actually the output of our algorithm. Okay, this algorithm can look a little bit complicated. There are a lot of steps, but don't worry. To understand how like SkiSign 2D works, you just need to take this as a black box. So the takeaway from this slide is that now we know that we can convert efficiently any ideal to an isogeny. And to do so, we need some kind of two-dimensional computations. We need computations of two-dimensional isogenies. And these are efficient because, there are efficient algorithms to do so. Okay, so now let's talk a little bit about the concrete design, the concrete like explanation of like SkiSign 2D. So the setup that we have is that we have like a prime p of the form c times 2 to the e minus 1. And this p should be roughly equal to 2 to the 2 lambda. We should note that a prime of this form is especially nice whenever you want to implement concretely the algorithm, because like you can perform arithmetic over the base field in a really efficient way. And that's the reason why we achieve these kind of nice results for like for the efficiency of SkiSign 2D West. And the other part of the setup is that we, as I was mentioning before, we have this special curve E0, and this is the curve with J invariant 1728. So now let's talk a little bit about how key generation works. So the first step is that you sample a random ideal ISK of large norm. Why do you want to do so? Because whenever you have an ideal of such a large norm, then you know that the corresponding isogeny is uniformly distributed among all the possible isogenies that you have in this setup. And for this reason, that's the reason why, since we can actually compute isogenies which are provably uniformly distributed among all the possible isogenies. And using like this trick and this piece of theory, we can actually show that the variant that we achieve is actually provably secure. And then once we sample this random ideal here of large norm, sampling this random ideal is not a big deal, can be done efficiently. Then we use the algorithm ideal to isogeny that I've described before, and we convert this ideal to an isogeny, phi sk, and then our public key will basically be the elliptic curve EPK, which is actually the codomain of the isogeny phi sk, and the secret key will just be the ideal ISK. Okay, so this is like the key generation. There are very few steps once you are willing to assume like that certain algorithms work as a black box. Now let's talk a little bit about the commitment generation. The commitment generation is really similar to the case of key gen. So again, you sample a random ideal of large norm. The reasoning is the same. Basically, you want this ideal to be really large so you can prove that the commitment curve is uniformly distributed in the supersingular isogeny graph. And once you sample this ideal ICOM, you convert it via ideal to isogeny to an isogeny phi com, and then your commitment will basically be the curve ecom. And now let's talk about the challenge generation. So here we have to introduce some constants. So let's recall that the prime p is of the form c times 2 to the e minus 1. So since I said that c is kind of a small integer, e, which is like the exponent of 2, should be roughly equal to 2 to the lambda. So should be roughly equal to 2 lambda, sorry. And echal, which is actually a constant which determines like the size of our challenge space, is roughly equal to lambda. So the first thing that you do when you compute this challenge isogeny And is that you compute a deterministic basis of the 2-to-d torsion over the public key. Then the challenge is basically just an integer in this between like 0 and 2-to-d each all. And then once you sample this integer chal will actually determine what's like the kernel of your challenge isogeny. And the kernel of your challenge isogeny is the group generated by the point ppk plus qpk scaled by the constant, by the challenge chal. And then, during the challenge generation, you just compute this isogeny. This is like an isogeny which is really efficient to compute, and overall, this procedure is like really, really fast. And now let's talk a little bit about like the most demanding step, which is the response generation. Andrea was talking about the fact that whenever you have like the two endomorphism rings, then you can actually find an isogeny connecting like the two curves. But now let's explain how you do so. So in this case, we have to introduce a new constant, and the new constant is like this exponent eresp. Eresp is chosen such that 2-to-d resp is larger or equal than 2 times the square root of 2p over phi. This may seem as a random, like a little bit of a random like value, but this value is fundamental because it ensures that our response algorithm works and never returns like a failure. So how does the response algorithm works? So the first step is that you compute an ideal associated with your challenge isogeny. Then you look at the ideal J, which is given by the dual of ICOM times ISK times HL. This is basically the ideal describing the isogeny connecting ECOM and HL, which is given by the dual of phi-com together with composed with phi SK and together with composed with phi chal. But of course, if you reveal that isogeny, you sort of leaking your secret key. So you don't want to do so. So once you have that ideal J, you compute another random ideal, IRESP, and the norm of this ideal should be smaller than 2-to-d resp. Given like the requirement on 2-to-d resp, we know that such an ideal will always exist. And by the fact that we sample like a random ideal, like your response isogeny will look like something which is completely random. And for this reason, you obtain like zero knowledge for the Sigma protocol, and in turn you obtain like all your security properties for the overall digital signature scheme. Okay, so the ideal IRESP, which describes your response isogeny, has norm Q. And now Q can be anything. But just for the sake of simplifying a little bit like the treatment of this algorithm, which is already complicated, let's assume that Q is odd. In this case, you apply the algorithm ideal to isogeny that I've described before, and you compute, you convert this ideal IRESP to an isogeny, and you also compute an auxiliary isogeny, as Andrea was explaining, of norm of degree 2-to-d resp minus Q. And then your response for this procedure is basically the evaluation of phi resp on the 2-to-d resp torsion, and the same for phi aux. Now let's finish with the verification algorithm. For the verification algorithm, again, a verifier should recompute the challenge isogeny, and then using like the data given by output during the response, you look at this kind of two-dimensional isogeny, which is described by like this matrix of isogenies. And one of the components of this matrix is actually the dual of the response isogeny. So if you can compute this isogeny, it means that you have successfully obtained an isogeny connecting ECOM and HL. And this is actually the gist of the verification. Computing this isogeny here, this two-dimensional isogeny, is really efficient because there exist efficient algorithms to compute so. And now the last slide. I have like 2 minutes, so I will leave the slide here as I take some questions. And what I want just to let you notice is that compared to like the SkiSign version, which is submitted to NIST, we have like a dramatic improvement on all possible aspects. aspects. So for instance, I mean, here I'm giving timings in million cycles. And let's just look at verify. For level 1, we move from like 39 million cycles to 9 million cycles in the case of like SkiSign 2D. And this makes, for the first time, we have like a version of SkiSign which actually falls in the realm of practicality. And yeah, so this is my last slide. Happy to take questions. And in the meanwhile, you can look at nice shiny numbers. Thank you.
Let's thank Luciano, and we are happy to take any questions. So there doesn't seem to be any from the audience. I do have a question. So when you say you use like the intrinsics, do you mean you are using vector arithmetic?
Sorry, why do the slides disappear?
But the last slide. Yeah, so optimize using intrinsics for the ice lake architecture. And do you know like what vector instruction set were you using?
To be honest, I'm not like taking care of like the implementation side of the like SkiSign, but here there are like people in this very room, like there are people better equipped to answer to this question. So maybe we can take this question offline and discuss it a little bit more later on.
Any other questions? Okay.
There is a question.
Here's one finally.
Hello. Good morning. Really nice talk. Just one question. Do you have any comments about the constant time?
Do you have, sorry, what?
Any comments about constant time?
Yes, I do. I mean, like the version that we showed here is the times that I'm showing here are actually do not refer to a constant time version of like SkiSign. I'm aware of like there is some work going on like potentially obtain like a constant time version of like SkiSign. So there are really promising results. And yeah, I mean, at the moment, this is what I can say, because I mean, like there is not much public work about this, but there are like people looking at this and try to have like a robust constant time implementation of like SkiSign.
Okay. Thank you.
Thank you.
Any other questions? Okay, well, let's thank Luciano for the very nice talk.
Can everybody hear me? I guess so. Looking at the vehicle. Okay, so I have a very good news for all of the audience. There are still 3 other variants of SkiSign to be seen today. And so you've seen with the magnificent talk of Luciano, SkiSign 2D West. Now you will see Ski Prime. So it's all of the variants that will be presented are more or less answering one question, but using different tool each time. And in the case of Ski Prime, we in fact didn't use the ideal to isogeny that was introduced in SkiSign into the West. We in fact used non-smooth challenge isogeny that may seem somewhat weird, but in fact, it's the heart of the mechanism. And this coupled with Cannes lemma and using a lot of very, very nice and very marvelous diagrams enables us to perform efficiently ski prime. So let me just give you a small idea on how. Let me just give you a bit of background. So in SkiSign, we were working often with, as explained by Andrea, with smooth isogeny. And therefore, as our isogeny was smooth, given a smooth isogeny, it was easy using some discrete logarithm to retrieve the ideal that was corresponding to this isogeny. But when our isogeny becomes non-smooth, for example, when our isogeny becomes prime, this becomes slightly more tricky, but there are solutions. And in fact, the solution we used in ski prime was first introduced by Leroux in his work on during VRF, and it was what we call a during VRF basis. So given Q, an unsmooth number, will during VRF basis of order Q will consist of 2 points, P and Q, that generates the basis of the Q torsion, such that you also have knowledge of the you also have knowledge of an endomorphism that maps P to Q, and finally you have knowledge of the ideal IP that corresponds to it is the ideal that corresponds to an isogeny whose kernel is generated by the point P. Why? So this may seem a bit arbitrary. Sorry. Is it better? Okay. So this may seem somewhat arbitrary, but in fact, using this, we can more or less perform. For any isogeny of degree Q, we can find very efficiently its corresponding ideal using this formula. And another very nice property is, as using isogeny, we can move our knowledge of the endomorphism ring. This method is also preserved through isogenies. And this is very practical. So the other object that we will use is what's called Cannes lemma. So we have talked throughout the previous two presentations about Cannes lemma. It's just the real name of this HD presentation. And it is extremely versatile, extremely powerful, and most of the greatest results in the last 2 years in isogeny-based cryptography are more or less the nice application of this lemma. Because so using more, the idea is, if you have this commutative diagram of this form on the left of the board, then this induces a dimension 2 isogeny of this form, and that you can efficiently compute using this kernel. There is actually a very specific thing that I wanted to highlight about the Cannes lemma. It's not only are you able to compute efficiently isogenies, but you're also able to compute efficiently push forwards of isogenies, which is very handy and which is a Chekhov gun that I will let here and that will be happening later inside this presentation. So we have now everything that is needed to explain ski prime. So similarly to SkiSign 2D West, or we take a prime number that is of the form a huge torsion of 2 times f, a small cofactor. But in addition, we also ask in ski prime that p minus 1 has a factor q, which is roughly of the size 2 to the lambda and prime. And on this q, we will compute on the curve E0, which was defined by Luciano just earlier. We'll define a during VRF basis of order q. Then, using something that Luciano called the fixed degree isogeny, we are for our key generation we'll just sample an secret key isogeny of prime order LK. But additionally to what was done in SkiSign, we will also evaluate through this isogeny ordering VRF. Problem is that if we let it like that, we will leak information about our secret isogeny. Therefore, we mask using a matrix this isogeny, and we therefore get that our public key will correspond to the codomain of our secret isogeny. So it's written EP, it's EPK. plus those the 2 points that are the masked image of through our secret isogeny, so R and S, while our secret key just consists in our secret isogeny and the mask that was used. The commitment is actually very similar. It's just that we don't have to do any evaluation over the during the RF basis, but this is how it's done. Now, for the challenge, contrary to every other variant of ski sign, our challenge is unsmooth. In fact, it is prime. So our challenge is in fact a point of point between 0 and Q. And this point defined using the point R and S uniquely a point which we call the challenge point. They're written CA, and such that this point CA is the generator of the kernel of our matrix. Now, given a small a, using the during the RF construction, you're able to retrieve efficiently the ideal that corresponds to the challenge. Then, using the LLL, we can therefore find the isogeny that links the challenge. We can find the ideal that corresponds to the smallest isogeny that links the challenge and the challenge curve and the commitment curve. Now, the problem that we have is that both the challenge isogeny and the response isogeny are in ideal. So individually, we are not able to evaluate them, but combined, we can. So we will, from now on, work with this challenge plus response isogeny, which is just the composition of both. Using our knowledge of the endomorphism ring over E0, we can efficiently evaluate it on the two torsion, and we'll just have to send this two torsion we'll just have to send as our response this two torsion. Now, the idea of the verification is actually quite easy. It's using Canny's lemma and the two torsion that we were given. We will represent this challenge plus response isogeny. But now we need to, as a verifier, we need to check that this challenge plus response isogeny in fact corresponds to the challenge plus the response isogeny. And how do we do that? Well, we do that, in fact, quite easily by just checking that the isogeny that we received is valid and that it maps the challenge point to 0. So it seems very easy. The main problem is that we need to find an auxiliary isogeny of degree 2 to the E minus QD in order to apply Canny's lemma. So in dimension 4, it is actually somewhat easy because we could take D such that 2 to the E minus QD would be the sum of 2 square. Then our auxiliary isogeny would be a trivial endomorphism of higher dimension. And the function f that we would use would be this monstrosity. But in dimension 2, it's slightly more harder. But it's in fact doable thanks to the fact that we are working with not just the response isogeny, but the challenge plus the response isogeny combined. Therefore, we have more or less no way to work to force D to have a nice value, but we can control the Q. You can control Q. And so the trick in ski prime is to say, well, what if we say that the degree of our secret isogeny was Q? Why does that help? That may seem random, but in fact, it enables a very efficient way to retrieve our auxiliary isogeny. So for technical reason, we need a second secret key isogeny, but this is not, in fact, not really difficult and given almost trivially by the definition. But as one of our secret isogeny is of order Q, we can then sample an endomorphism over E0 of degree D times 2 to the E minus QD. This therefore, endomorphism therefore splits into two isogeny, one of order D, the other one of order 2 to the E minus QD. But you see that here on this part of the diagram, you have half of a case where you could use Canny's lemma. So by applying Canny's lemma, you're able to efficiently evaluate the push forwards of the isogeny that you computed, and therefore you have a nice way to obtain a way to compute the auxiliary isogeny whose domain is the public key, and the codomain is a curve which is the ecom. So nevertheless, this induces a few subtleties on the keygen and the verification. I'll just briefly mention what are the subtleties on the verification part. It's that you will be given the composite, so the evaluation on two torsion of the dual of the auxiliary composed with the challenge plus response isogeny, and you are able to compute a function f, which is given here. The one thing is, if you look at f, you see that you don't have the challenge plus response isogeny. You have the dual of the challenge plus response isogeny. So therefore, it's not really practical to evaluate the challenge point and to see that it is equal to 0. But so in order to make it to have an efficient verification, we have to additionally give to the verifier a point v, which is in fact the evaluation through the auxiliary isogeny of the challenge point. And using this point, he will be able to check that the challenge plus response isogeny is in fact valid by evaluating f over the point 0 f and checking that both z1 z2 are following those equations. The reason why this works is that we are not checking that the challenge plus response isogeny is valid. We are sends the challenge point to 0. We are checking that the push forward of the challenge plus response isogeny sends the image through the auxiliary point to 0. It's really a technicality, but it is important to explain the capacity of ski prime. But so this is more or less the greater view of ski prime. So in order to work with ski prime, we have to work with ski prime primes, which are p that are of the form that I explained priorly. Those conditions may seem somewhat difficult to find, but actually they can be found in polynomial time. And in our paper, we propose four different numbers for different level of security. Those prime numbers were the one that were given us that had the smallest cofactors, and that were therefore the most interesting in terms of security per cost. Then, so using the standard field schema, we can construct with ski prime a quantum resistant signature scheme. You will see that comparatively to ski sign or ski sign HD, ski prime is less has a greater signature and greater public key. This is in fact due to the fact that we have to share this point, those 2 points RS in the public key, and we are sharing T, U, and V that are T, U, and V that are either hard to compress or that are uncompressible. But nevertheless, this is still more compact than more or less anything that is not based on isogenics. And so finally, we implemented a proof of concept using Sage Math of ski prime, and you see that compared to après-ski, which was an implementation based on the original ski sign, you see that the signature is quite more efficient. And compared to the verification of ski sign HD, which used dimension 4 isogeny, the verification is in fact very much efficient, and there is still a lot of room for improvement, as many tricks were not implemented inside this mechanism. But to finish and to give a greater conclusion on my talk, I will say that with those new 2D representation, we are really arriving at an age where it has never been so easy to explain and construct ski and work with ski sign. Thank you very much for your attention.
Thank you, Max, for the great talk. Do we have any questions? So my question is, you mentioned that this is only Sage Math.
Yeah.
Is there a planning, like something in the works for a serious implementation?
Yes, it's in the work. It just there were some technical problem on the 2-2 isogenies that needed to be fixed. That was a bit technical, but it's in the work.
I see. I guess there's the obvious question is how does the techniques here interact, combine, or like with the other ski sign 2D variants?
You mean combine or?
Like I mean, you use different techniques, and can any of those be added together?
Could maybe. Actually, it's a very good question. We could maybe save some computation times using the VRF basis to retrieve the challenge isogeny in some ski sign, but otherwise, the ideal to isogeny is a very, very powerful mechanism. That all ski sign, all what ski prime does, it's more or less working around the prime. So we found a way to zigzag through the technicalities, and we are at an equilibrium where this works. But it's the difference between following the path or just going straight and finding a result that makes everything somewhat trivial.
Thank you. Any other questions? If not, let's thank Max for the great talk. And we will have Kohei Nakagawa, our next speaker. So the last of the ski sign 2D challengers. So let's welcome Kohei.
Okay, so I will talk about ski sign 2D East, the final variant of ski sign 2D in this talk. So, okay. First, I will give some background of my study. So, in 2020, an isogeny-based signature named ski sign was proposed, and it is submitted to the next additional signature competition. And it has very short signature size among the competition, among the candidates of the competitions. And in 2022, the several attacks on the SIDH using higher dimensional isogeny was found. So from this time, many protocols using higher dimensional isogeny have been proposed. And one of such protocols is ski sign HD, as you know. So ski sign HD is a signature scheme using 4 or 8 dimensional isogeny for its verification. So it has shorter signature size and smaller signing cost compared to ski sign. However, it has higher verification cost as it uses 4 or 8 dimensional isogenies. Okay, so here's our contributions. So we first made a new algorithm named generalized random isogeny images, which computes a random non-smooth degree isogeny from any of the curves. And using our new algorithm, we made a new signature scheme named ski sign 2D East, and which only requires 2-dimensional isogeny for its verification. So we achieved the speed up of the verification. By the way, the original ski sign 2D East was proposed by me and Onuki, but there was a security issue found by Kastrick et al. And they also proposed a method to repair the issue. So today's talk is about the joint work with them. I mean, the repaired version of the ski sign 2D East. So now we go into some preliminaries. And here is the notations I used. So lambda is security parameter, and P is large prime, such that P equals 3 more than 4. And then P squared is final field of order P squared. And E0 is a curve defined over P squared, defined by this form. So E0 is known to be supersingular. And B sub P infinity is the quaternion algebra defined by this relationship. Okay, and N over alpha represents a reduced norm of an element alpha. And finally, O0 is the maximum order of B sub P infinity of this form. Then the O0 is known to be isomorphic to the endomorphism ring of the curve E0. So now I show an important algorithm named to represent integer. So this algorithm takes as input an integer m larger than p and output an element gamma of O0 satisfying n over gamma equals m. So the point is that the corresponding endomorphism of E0 has a degree m because gamma has a norm m. So this algorithm outputs the endomorphism of E0 of given degree m. And here is another algorithm named special Hill norm that is a kind of the generalization of to represent integer. So it takes as input the left O0 and the right O1 ideal I and an integer m, satisfying these several conditions, and it outputs gamma in O1 satisfying n over gamma equals m. So when we see this algorithm from the empty curve side, this algorithm takes as input the isogeny phi from E0 to E1, and then it outputs the endomorphism of E1, whose degree is the given m. Okay. So next I give about the use of two-dimensional isogeny. So here I use this diagram. So where the psi1 and psi2 are the isogenies of degree d1 and d2, and let large D equals d1 plus d2. And F is the composition of psi2 and psi1 hat, and P1, Q1 is a basis of d-totient subgroup of E1. And finally, P2, Q2 is the images of P1, Q1 under the isogeny F. So under this situation, if we know these 6 values, and then we can compute E and psi1 and psi2 by just computing one DD isogeny. So DD isogeny means the two-dimensional isogeny of degree D. And especially when the D is the power of 2, then DD isogeny can be seen as a chain of 2 to isogeny, so we can compute it very efficiently. Okay, so in this talk, I will denote this algorithm by Kani evaluation. So this algorithm takes these inputs and returns E and psi1 respectively. So next, I explain an important algorithm using Kani evaluation. So this algorithm takes relatively prime 2 integers, small d and large d, with a finite subset of E0, satisfying these conditions. Then this outputs the codomain of a random D isogeny tau from E0, so the red one, with some point images tau of S. So the point is, so this algorithm essentially computes a given degree isogeny from E0, even if the degree D is non-smooth. Okay, so we can compute non-smooth degree isogeny from E0 by using this algorithm. And here is the concrete steps of this algorithm. So we first use full represent integer with this input. So we obtain the endomorphism of E0 of degree small d times large dimensional D. So we can see this endomorphism as the composition of D isogeny tau and large D minus small d isogeny rho. Okay, so now we can use Kani evaluation on this diagram, and we now obtain the curve EA and tau and rho, and it finally returns the curve EA and tau S. Okay, so as a final preliminaries, I want to explain about ski sign HD. So as you already know, ski sign HD is based on this diagram, where tau is secret key and size commitment, phi a challenge, and sigma is the response isogeny. Okay. Yeah, and in the verification of this protocol, the verifier should determine whether the sigma is the Q isogeny from E1 to E2. And to do so, the verifier first prepares a two-dimensional isogeny, large omega of degree 2 z minus q. So like this. And then the verifier tries to use Canyon variation on this diagram. And in this time, the verifier need to compute the four-dimensional isogeny because each isogeny is two-dimensional. Okay. So now I go into our contribution. Okay, so how to reduce the dimension of the protocol? So in SkiSign HD, they use two-dimensional isogeny of degree 2 z minus q, and as a result, the verifier needs to compute the four-dimensional isogeny. So the simple idea to reduce the dimension is to use the one-dimensional isogeny like this instead of the two-dimensional isogeny large omega. But to compute such an isogeny is not so easy. So for example, the first idea is to use Bell's formula, but we cannot use this formula because the target degree is not smooth. Okay, so recall that Bell's formula can only compute smooth degree isogeny. Okay, so we cannot use Bell's formula. So another idea is to use the random isogeny images because this algorithm can compute non-smooth degree isogeny. However, this algorithm can only compute the isogeny from E0. Okay? But we now want to compute the isogeny from E1. So we cannot apply this algorithm either. So we need to construct some new algorithm to compute this isogeny omega. Okay, and we constructed new algorithm named generalized random isogeny in this. And this is the main difference from 2D West because in the 2D West, they use ideal to isogeny algorithm. On the other hand, we use generalized random isogeny images to compute the isogeny omega. So here is a setting of a protocol. So P is the prime of this form where F is some small integer and A and B is is approximately equal to the security parameter lambda. And we also use E0 and O0. So now I want to explain our new algorithm. So this algorithm is a kind of a generalization of the random isogeny images. And the main difference of this algorithm is that we use special Euler norm instead of represent integer in step 1. Okay, so the blue one is the difference from the original random isogeny image. So we need additional input, that is an isogeny from E0 to E1, and we require that additional two constraints on the degree D. Then we first use special Euler norm with this input and obtain alpha of degree small d times large limit small d. But this alpha is the endomorphism of E1, not E0. And then we use Canyon variation and obtain f and tau and rho and returns f and tau best. All right. So now we can compute the isogeny from E1. But we cannot directly compute the isogeny omega by computing our new algorithm. The reason is that from our setting and from the constraint, from this constraint, we have this constraint on D. And this constraint is too strong. I mean, the lower bound is too large because we want to compute omega of degree 2 to the minus q that is approximately equal to the square root of p. Okay, so to solve this problem, we instead compute the larger degree isogeny, so the q times 2 to the minus q isogeny. Okay, then the d will be q times 2 to the minus q, and that is approximately equal to p. So this satisfies these conditions. Okay, and now we obtain Q times 2 to the MSQ isogeny, and then by using cannibalization again, we obtain Q to the MSQ isogeny. But unfortunately, there is another problem. So as I said before, there is a security issue on our new algorithm. So I want to talk about this. So to execute our new algorithm with this input, we require these 3 conditions. And the problem is in the third condition. So from the third conditions, the degree n depends on the degree q, right? And in our protocol, the degree n must be kept secret for the security. On the other hand, the degree q is published as a signature. So from one signature, the adversary can learn 1 bit information of the degree n. So this is problem. Well, to avoid this issue, we modified our algorithm. So we first use the degree n of satisfying this condition, and we use the third conditions like this instead of this equation. Okay, so now the degree n does not depend on the degree q, right? And here is the modified version of our new algorithm. So our algorithm has 2 cases, and in the first case is same as in the original randomizer algorithm. So the difference is in the second case, where this value does not equal to 1, but equal to -1. Okay, so in this case, we cannot use the special Eichler norm with the input m over q. And instead, we use this input, m over q over 3. And from these 2 conditions, we have this equation. Okay, so we can use m over q over 3 as the input of special Eichler norm. And then we compute additional random 3 isogeny and compose it with the alpha prime. Now we obtain alpha of degree m over q, right? And then we use cannibalization again and obtain f and tau rho and retains f and tau s. So this is the modified version of our algorithm. So here is our protocol. So as for the commitment, challenge, and sigma, we compute them almost same as in SKI-sign HD. So we additionally compute the isogeny omega by using our new algorithm. That's all. And in the verification, we just use cannibalization on this diagram. Okay. And here is performance. There is a proof of concept implementation derivative. So, okay, and here is signature size compression. So as you can see, the signature size of our protocol is similar to SKI-sign to the west. Okay, and that is also smaller than SKI-sign. So if we compare our protocol to SKI-sign to the west, our protocol is a bit more efficient than to the west because the number of 2 isogenies is smaller than to the west. On the other hand, SKI-sign to the east needs stronger assumptions compared to the west. So the security is not better than to the west. So for example, we need to assume the uniformity of the isogeny omega computed by our new algorithm. So here is the conclusion of the future work. So as a conclusion, we construct a new algorithm, a new signature scheme using name to the east using our new algorithm. And the computation cost is smaller, but the security assumption is stronger compared to the west. And as a future works, we are trying the further optimization of our protocol. And we want to we want to optimize implementation in C. So that's all. Thank you for your attention.
Any questions for Kohei? I guess I have the same question as the last one, which is any of the other ski sign 2D techniques usable towards helping ski sign 2D East?
Use other variant of
Yeah, can you borrow
technique?
anything from the?
Maybe that. It's a difficult question. Maybe we can, but I'm not sure for now.
Okay, let's take that offline.
Mhm.
Yeah. Okay, so thanks, Kohei, for the great talk. Now for our last speaker of the isogeny session, Hiroshi Onuki. And we can say that this is sort of like the genesis of the other ski sign talks.
Is this on? Oh. Okay.
All right, so let's now welcome Hiroshi.
So thank you for the introduction. I will talk about ski sign, but I will talk about an improvement of ski sign 1D. And this is a joint work with Kohei Nakagawa. Okay, so here is an overview of my talk. We propose an ideal two-isogeny algorithm using two-dimensional isogenies. I mean, our algorithm uses Kani's lemma. And our algorithm can be used to compute almost all isogenies appeared in ski sign except for challenge isogeny. And our algorithm improves the efficiency of the KRPT-based ski sign, I mean ski sign 1D. But in this talk, I will focus on the computation of the response isogeny. And here is our setting. As the previous talks, P here, P is the characteristic of the base field, and E0 is the specialty curve, and O0 is the maximal order of the quaternion algebra isomorphic to the endomorphism ring of O0. And in this talk, we denote the isogeny corresponding to an ideal I by phi sub I. And our purpose is to compute the isogeny corresponding to J, an ideal J, whose norm is to the power of K times F. So we want to compute the horizontal isogenies. Here we divide phi j into K parts because the kernel of phi j is not FP squared rational, so we use small isogenies whose kernels are FP squared rational. So our goal is to compute phi j1, phi j2, and to phi jk. So here I will explain why we need to discuss how to compute these horizontal isogenies. The first part is easy, so because we can compute the kernel of phi j1 by using this condition and this group. So I mean this group, the 2 to the F torsion subgroup of E0 is a p-squared rational, so we can compute the kernel, the kernel of phi j1 by using phi I, and phi I is given. But for the next isogeny, we cannot use the same way because the kernel of phi j2 is expressed by this form, and the 2 to the 2F torsion subgroup of E0 is not a p-squared rational, so we cannot compute this kernel efficiently. So we need to some techniques for solve this problem. The solution proposed in the original ski sign paper is to use another isogenies from E0 to E1, E2, and so on. And these red isogenies have odd degrees. So how to compute these isogenies? These isogenies correspond to ideals II, which is equivalent to the product of I times J1 and I times J1, J2, and so on. And these red isogenies are computed by Berg's formula. Then, by using these red isogenies, we denote this by phi II. Our kernel, the kernel of phi j plus 1 is represented by this form. So we can use the first red isogeny. By using this isogeny, we can compute the kernel of this, and then we compute this, then we obtain the kernel of this. So we can compute for these isogenies. So, but for this, we need to restrict the form of P. Since phi I is computed by Berg's formula, we require two things. The first is the degree of phi I should be smooth, and the second is the kernel of phi I should be fp squared rational. So we require that p squared minus 1 has a smooth odd factor t, and the t is of size about p to the 1.5. As a result, the degree of phi I has large prime factors. In particular, the degree of phi I is equal to t squared, and the computation of phi I is not so efficient. This bound, so the bound to the 1.5 was improved by these people to the 1.25. Despite of this improvement, T has rise prime factors. So for example, the Nistler security level 1, T is this form, and T has large prime factors greater than 1000. So our idea is to replace inefficient T isogeny with two-dimensional isogenies. In particular, we use change of two isogenies. These isogenies, the computation of these two-dimensional isogeny is relatively efficient compared to T isogeny. As a result, we do not require T divides p squared minus 1, and we can use more simpler form P. So our P is of form, this form, and where 2 to the F2 is greater than P squared, and T is a small integer. So here is our setting again. So from now on, we restrict compute a small part of our diagram, because if we compute this 2 to the 2F isogeny and this odd degree isogeny, then we can compute the kernel of the next isogeny. So from now on, we will focus on how to compute this isogeny and this isogeny. So the first part of our algorithm is to compute phi j. This is computed by Bayes' formula because the kernel of phi j is this, and this is scalar rational, so we can compute this easily. And the second part is to find integers a, b, and an endomorphism beta in I times j. These objects satisfy first d defined by this form is odd, and a square time plus b squared plus d is 2 to the 2f. These integers and endomorphism can be computed by the rest enumeration algorithm and Kronecher's algorithm. I mean, we use error algorithm. And then we define ideal I prime as this. Then I prime is equivalent to I times j. I mean the corresponding isogeny is an isogeny from E0 to E prime, and the degree is d. And we define beta as this. So beta is the composition, this isogeny and this isogeny and this isogeny. The third step is to compute the restriction of this isogeny phi I prime on 2 to the F2 torsion subgroup on E. This means we compute the image of a basis of 2 to the F2 torsion subgroup on E and phi I. For this, we use this relation. This means the composition of the dual of beta phi I and j is equal to phi I multiplied by this value. And let PQ be a basis of this torsion subgroup. And this is F squared by our setting. Then so we multiply these points by this value. Then we can obtain a base of this torsion subgroup. And from this relation, we can evaluate the image of this point and phi I prime by using this. So we obtain the restriction of phi I prime on this torsion subgroup. Finally, we apply Kani's lemma on this diagram. Here, the sum of degree, the degree of this plus degree of this is equal to f squared plus b squared plus d. So this is equal to 2 to the f2. And we have the restriction of this isogeny on this subgroup, and we can evaluate this endomorphism. So we can apply Kani's lemma to this diagram, and we can compute this isogeny. This is what we want to compute. So here is a summary of our algorithm. So again, first we compute phi j by using Bayes' formula. And second, we find a b and beta suitable for Kani's lemma. And third, we compute the restriction of this isogeny. And finally, we compute this isogeny phi prime by using Kani's lemma. So from now on, I will explain the impact on ski sign by our algorithm. So let's consider the needs-less security level 1. Our estimation shows that the computational cost of a isogeny is at least approximately equal to the cost of a 2 to the F2 to the F2 isogeny. And the numbers of these isogenies appeared in computing key generation and signing in ski sign security level 1 is here. So we can expect that the key generation time is at least 2 times faster, and the signing time is at least 3 times faster. Okay. And at a higher security level, the impact is more significant because the cost of computing T isogeny is the cost of computing T isogeny increases rapidly more than the cost of two isogenies. Okay, so finally, I'll conclude my talk. We propose an isogeny to ideal to isogeny algorithm using two-dimensional isogeny. And our idea is to replace the isogeny with two-dimensional isogeny. And this improves the efficiency of ski sign. But I should mention that other higher dimensional variants explained in the previous talks are more efficient than our improvement. And I should also remark that there are other ideal to isogeny algorithms using two-dimensional isogenies, including the algorithm in ski sign 2D West explained by Luciano in the second talk. And finally, I mentioned that I believe that finding new application of these algorithms, including our algorithm, is an important future work for isogeny-based cryptography. That's all. Thank you for your attention.